machine code.
Thank you. Can you hear me? Yeah, okay. So that's a very long title, but hopefully you'll get every word of it by the end of my talk. So this is joint work with Yuting Wang and Xiong Xiao from Yale University. So this work is in the context of verified compilation, and in particular in the context of the CompCert compiler. So CompCert has been around for more than 10 years now, and is a verified C compiler written with the code proof assistant, going through a bunch of intermediate languages, all the way down to assembly. There has been a large number of extensions to CompCert going out. So for example, CompCert TSO using a weak memory model instead of the CompCert memory model. CompCert S is another extension that gives defined semantics to more programs. Some works try to give a more concrete view of the stack in CompCert. So in particular, they merge the stack blocks into a finite stack region at the end. At the assembly level, and other work focus on compositional compilation, so there are a number of works in that direction as well. But what remains open problems is to have sort of all those things at once. So we want to have verified compilation down to machine code, which I'll define later, but it's lower level than CompCert assembly. We want to have a complete extension of CompCert, so most of those extensions don't include most challenging optimizations, such as function inlining or tailcall recognition. And we want to have some flavor of compositional compilation. In particular, we want to be able to compile heterogeneous modules, so with some parts written in C and some in assembly. Right. So our contribution is a solution to that. So what we call stack-aware CompCert, which is a version of CompCert which addresses compilation to machine code. We support all of CompCert compiler passes, so included the challenging optimizations, and we provide a flavor of compositional compilation. So brief primer on CompCert and how its memory model looks like on a simple example. So we have a swap function with parameters here and a main function. And at the C level, the way the memory model looks is we have one block here per local variable or function parameter. And what can we say about that? Pointers are encoded as pairs, where the first component is a block identifier, and the second component is an offset within those blocks. So that's at the C level, and during compilation, that evolves in the following way. So those are the blocks that we show in the previous slide, and so I selected a subset of CompCert languages where the stack structure changes. So some of those blocks can be removed from the memory, then they are merged together in a single so-called stack block. And then at the assembly level, you introduce some new data that wasn't here in the higher level languages, such as the return address of your function, the callee save registers, and so on. All right. So one thing we can notice is so the stack frames at the assembly level for those functions are still in distinct blocks, which is unlike actual assembly code where we have continuous stack region. Right. So what we propose is to modify CompCert memory model and introduce what we call an abstract stack, which is a structure that reflects the structure of the concrete stack. All right. So it's going to be a list of abstract frames, one for each function, and in each abstract frame, we're going to store useful information. Namely the size that the stack frame will occupy when it's compiled at the assembly level, all right, so that we know how much stack space it will use concretely. We'll also record which blocks are part of that stack frame, and what we're going to call stack permissions, so which locations in those stack blocks are public or private. So if we take the example of the functions we introduced earlier, at the C level, we have this kind of abstract frames with several blocks corresponding to the function local variables. And the permissions here are green, meaning public, because those are stack allocated data that can be modified by others. And we also have this number here, 32 bytes. That's the amount of stack space that this function will take. At the assembly level, this looks like this, and we have this portion that corresponds to stack allocated variables that is still public, but the return address and the call-save registers are private to that function and shouldn't be modified by others. So at the C level, the abstract stack is going to look like that. So with two components, one for each function, one abstract frame for each function, and everything is public. At the assembly level, well, we still have two components, but now we have private permissions here. All right. How do we manipulate this abstract stack? So we introduce some abstract stack primitives, so operations on the memory model that makes this abstract stack evolve. And there are two of those. So push frame to, that is going to be called that function call, that, well, pushes a new frame. And an important thing is that this only succeeds if once we add this new frame, the sum of all the frame sizes is lower than some threshold, which will be the size of our concrete stack in the end. So because of that property, we are going to be able to merge stack blocks together in the end into a finite region of the stack. And at function return, symmetrically, we're going to call pop frame, which will, well, pop this frame, and we'll end back at the same situation we were in the end. So now that we take into account stack usage, we have to preserve stack usage across compilation, right? Because we want to prove the correctness of our compiler. Okay, so what does that mean? We want that the source stack at every point in the execution of the two programs, the source stack is larger than the target stack. So for regular compiler passes, the structure of the stack is going to be the same before and after the pass. So this is what this drawing is trying to say here. And then so the size of the source stack is the same as the size of the target stack. So that's easy in that setting. If we look at function inlining, so well, we have function f that calls a function g here, but it's inlined in the after inlining. Then the source and target stack look like that, and it still works because, well, the sum of those frame sizes is still larger than the target stack, right? Problematic example is when we consider tailcall inlining. So in the source, you have a tailcall to G, right? And this tailcall is inline into just the body of G here. So what happens in that case? So before we do the tailcall, we have F on both sides, no problem. And when we do the tailcall, we're going to remove the frame for F and replace it with the frame for G, right? And we're in that situation where we want to compare, well, the stack that's made of a stack frame for G and stack frame for F, and we cannot really compare those. So the solution that we have is we actually keep information about the frame for F, the function from which we tailcalled, and what we will consider to be the size of the source stack here is going to be the maximum between the sizes of those two frames. All right, so actually the structure of the abstract stack is not just a list of abstract frames, but it's a list of abstract frames, so which is going to look a bit like that, where a vertical arrow means a regular function call, and an horizontal arrow means a tail call that we still record. All right, and so a sequence of horizontal calls, we're going to call that a stage. So this abstract stack is actually a list of stages. All right. Once we are here, so we have a compiler with a stack over compiler, and we have some information about the size of the stack. So this is how the memory model in CompCert assembly looks like. And we have those stack blocks, and we're going to go to a new language that we call single stack assembly, where the stack is, well, a single region. And so this compilation pass is possible because of the invariant that we have on the size of the stacks. Once we're here, there are pseudo instructions in CompCert assembly that we can get rid of now that we have a single stack. I will say a few words about that just later. And then we merge all the memories for all the code of all functions and for the globals as well. And then we use the rock salt works, which provides an encoder function for x86 instruction, and we encode the instructions as just bytes, and we end up with the program living in just plain memory, which is closer to a realistic machine. All right, so let's talk a bit about those pseudo instructions. So when you do a function call, the call instruction in CompCert assembly, its semantics uses a pseudo register array to stop the return address of the function, right? Whereas in what we call real assembly here, or what we expect of the semantics of actual assembly, would be more just push the next PC on the stack directly. But this push is actually in CompCert assembly performed later in the callee, within a pseudo instruction alloc frame that's introduced by the compiler. Okay, so if we want to go to compile further down and have a one-to-one correspondence between CompCert assembly instruction and the assembly instruction we actually emit, we need to do quite some work to relate those sequences of steps together. But so we do that, and we get rid of the pseudo register array and go to a more realistic semantics. And so this alloc frame instruction, we can get rid of it also entirely and replace it with just pointer arithmetic on RSP. So in CompCert, we couldn't do that because pointer arithmetic on different blocks doesn't work. All right, so this is something we can do now. Whoops. Another aspect of this work is related to those stack permissions that I talked about earlier. So here we have, so in green and red is whether this location is public or private, and in blue is whether it's accessible at that point in the memory. So for example, at the beginning we're in the main function and there are some locations that are private, but I can access those because I'm currently executing the main function. So those are my private data, so I can access it. And when you do push frame, well, what's in the private region of the main is now unreachable because we're in the swap function and we shouldn't be allowed to modify private data of the main function. But now we can access all of swap's private data and we get back to the original situation in the end. So accessible locations are either locations that are in the top frame, whether they are private or public locations everywhere on the stack. So we apply that to contextual compilation, which is a flavor of compositional compilation, which allows to mix programs that are written in different languages, right? So the idea is when a function f calls another function g, the private regions of f shouldn't be modified during the call to g. And so that's what the stack access policy that I described here enforces. So we can remark that programs, so think of G, if it's compiled from C with CompCert, it will automatically comply with that policy. But this is more interesting when we consider that G could be handwritten assembly code, and that characterizes whether it is acceptable or good assembly code. So we apply this principle to CompCert X, which is an extension of CompCert that was developed at Yale in the context of the Certicos project, which is a formalization of operating system kernel. And with that compiler, they built, well, Certicos. Okay. So let me compare a bit with the other extensions of CompCert that I listed at the beginning of the talk. So first is, well, vanilla CompCert, which targets the CompCert assembly language I presented. So the completeness column means that does it support all of CompCert passes, so obviously CompCert is complete. It supports separate composition since PLZA 16. And it's this amount of lines of code. And in bold here is our extension where we target machine code. We support all of CompCert's optimizations, and we have this contextual compositionality. So this took a bit less than a year and about 50,000 lines of code. So if we want to compare a bit, so this quantitative CompCert targeted single stack ASM and not machine code. Some optimizations were missing, and there was no compositionality. Compositional CompCert gives a more general compositional theorem, but the target is still CompCert assembly, and some optimization are missing. I might not go into the details for all of those, but we are quite happy that we go to machine code and we have all the CompCert's passes. To conclude, so we developed stack-aware CompCert, which is a complete extension of CompCert. It goes to machine code, so in particular we have a finite size stack. Our memory layout is closer to actual assembly, to actual machine code, and so that in that process we reduce the unverified part of the compiler. As I said, our extension is complete, and we support some flavor of compositional compilation. As for future work, so we'd like to port that to other backends. So currently, we only support the x86 32-bit backend because we rely on the rock salt instruction encoder. But apart from that, we foresee no problem in porting to other backends. And another thing would be to define a stack analysis or a verification framework to reason about how much stack a program uses, so as to prove that programs have defined semantics. Thank you.
Okay, so we can take questions from the audience or again on Slido. We have a question from the audience first. Let's start with Catalina, if we can.
Hello. So it's really great that you extend the verified part of CompCert to the syntax of machine code and a semantics that's closer to machine code. There still seems to be a gap in that people expect the semantics of machine code to be, well, it works with integers, there are no pointers, and in particular for the heap. So how do you expect that you can get all the way, or someone can get all the way?
So I didn't get what part you said is missing.
Well, the fact that you still have abstract pointers, in particular for the heap. So, and yeah, that's not x86 or whatever machine semantics.
So we don't do anything special for the heap. So if you're referring to CompCert's malloc thing, we don't use, we don't.
No, I would expect that at some level, okay, in the future, one could get to the real x86 or machine semantics in which pointers are integers, yeah, and the memory is one big block, right? How far are we from that, and can your work extend to that?
So the memory is just now one big block, and pointers are just pointers within that block, but there are still abstract pointers in the very last language I showed. This one here, so we have just one big block, that's the memory. No, that's the whole memory.
Also for the yes. And is this last part very fun? Yes. Well, we build our own memory allocator. Memory allocators are very fun. Honestly, it's just some global memory, and you allocate.
Other questions from the audience? Yeah, we have one from Slido. What would it look like to interoperate with a language with a different convention, for example, CPS?
Right, so what happens is when you call a function, you set up the abstract stack so that certain parts are protected. So you would just have, if I understand the question correctly, to set up the right protections. And so, yeah. So the memory model enforces that the red parts here cannot be touched when those locations are not accessible. So I would say so. Yeah.
Okay, let's think Pierre one more time.